Good morning. We are going to do some basics on functions, domain, range, and continuity. So we have our technical definition of function with domain and range. And as we're looking at functions, we can see this a couple of ways, both graphically and numerically. Here's an example showing the difference between a function and not a function. If we take a look at the function side, we can see every x value has a unique y value. So if I'm looking at every single x value, I don't see anything that is repeated. I also don't see anything on the x column that has x, let's say for instance, having multiple x values at 1. It's only one x value at 1. So I can look at this and I can say, okay, the x value is going to one y value. So x value goes to 1 and only one y value. Different from when I'm looking at not a function. So if I thought of that same concept, the x value goes to 1 and only one y value, well, here's where it fails. See the x value of 1, and I'm noticing it's going to 2 different y values. Okay, that's where the function breaks down. The x value does not have a unique y value. So we want to be careful, because I'm sure you're also looking and saying, well, but what about this? What about the y? So I can see a y value here. That's okay. That's fine. I'm still looking at this. The x value has a y value. X value here has a y value. That's okay. All right. The issue becomes with the 1, because now the 1 doesn't have a unique y value. That's how your function, or that's how you're going to determine if the function is not a function. Graphically, if it is a function, we have different visual tests. So if it's a function, it would pass the vertical line test. Meaning, if you were to draw a vertical line on your graph, if you were to draw a vertical line on your graph, it would only touch your graph one time. If it touches more than one time, then it will fail your vertical line test. Okay. Different ways that we can see functions versus not functions, and now we're also going to connect it with domain and range. This first one is definitely a function. I can see every x value has a unique y value, every y value has a unique x value. Not only is this a function, but this is something that we would call a 1-to-1 function. Extra special, where not only does it pass your vertical line test, but it also passes your horizontal line test. If it passes both, then not only do you have a function because it passed the vertical line test, but you also have what's called a 1-to-1 function. Okay, if we look at the second one, well, we would have to say, nope, this is again not a function. Okay, and our reason is becoming right from here. I can see I have an x value in my domain going to 2 separate y values in my range. That is going to then fail, if we thought about this graphically, that would fail that vertical line test. Looking at example 3, this is a function. Okay, so again, probably the place that we would want to take a look at is this right here. Well, this is okay. I can still say every x value has a y value and only one y value. And the key here is that it has only one y value. Okay, so we're back on this example 2. It had a y value, but it had 2 y values. We don't want that. That's how it's going to fail being a function. Okay, so now if we need to take a look and find the domain, one algebraically, we'll check it graphically, and then we're also going to check it for the range. Okay, so when looking at domain, there are 2 places that you can have restrictions. One restriction is going to be under a square root, and that's what we have here. And we know that any value under the square root has to be greater than or equal to 0. So to start this problem off, I would say, okay, take your value that's under that square root and set it so that it has to be greater than or equal to 0. So I want to solve this equation, and if I solve this, add 4 to each side, and I would see, well, then x has to be greater than or equal to 4. This right here, that's your domain. You have now found your domain. So if we were to write that in bracketed notation, because I have that equal to, I could say your domain would have a hard bracket at 4, because that's going to include 4, and then it would go all the way out to infinity. Now I'm going to put a soft bracket or a parenthesis at infinity. You'll always have soft brackets there. That's not one value. Okay. Now it says we want to graph it, and we want to find the range graphically. So if we flip over to our calculator, I can see on the calculator, looking at both the graph, I can see it hits at 4, it includes 4, and it goes on in that positive direction forever. You can also check that by going to your table. Control T will get you your table, and I can see if I look at that table, I have errors of 3, but as soon as I get to 4, it includes 4, I have a value, and that's what we're looking for. Now if I look at the range is always your y value going up and down. I see it starts at 0, that's my lowest possible value, and it's going to go up and up and up and up forever towards infinity. So if I were to write the range, I would say, okay, so our range starts at 0. I want to include 0, so again, hard bracket. And then it goes out to infinity, so again, soft bracket. Okay. Other place for a domain restriction, second domain restriction here, is you can't have 0 in the denominator. Okay, so your denominator cannot equal 0. No good, no bueno. So you're going to find that denominator that we have, x plus 2, and we're going to say, okay, you can't equal 0. I know that that's not going to be possible. So if I solve, subtract over the 2, I'm going to find x cannot equal negative 2. Okay, so I can have every other value but negative 2. So when I'm writing my domain out, every other value, meaning I can go all the way down to negative infinity. My issue happens at negative 2. Okay, so I don't want to include negative 2, but I can include every other number super duper close to it. So the way I would represent that is, again, soft bracket or a parenthesis. That's saying don't take negative 2, take everything else around it. Now I can also go on the positive direction. So I'm going to combine that with a U, a union, and again, a soft bracket at negative 2 out to infinity. So this is symbolically representing basically can't equal negative 2. And if we were to go to our graph, we could take a look at the graph and say, all right, well, what does that look like graphically speaking? All right, well, at negative 2, I can see there is an asymptote at negative 2. There's no value at negative 2. So my graphical representation satisfies and supports my algebraic. When you're looking at the range, so now again, your range is your y values, you want to think to yourself, okay, I want all of the y values that possibly exist. Well, this one's kind of a funky little graph. So I had gone through and I found my max and my min points on these. And if I'm looking at this, I can see, well, from the bottom, always read bottom top when you're doing range. Every value from the bottom, negative infinity, all the way up to negative 9.66, and now that's going to be a rough estimate, is going to be included. Now I have this huge gap in between. And my next y value that I come up to would be this minimum value of a 1.66. And it extends forever in the positive infinity direction. So for our range value, okay, again, starting at negative infinity, so I would have a soft bracket, and it would go up to, and it would include 9.66. Now I know it's a rounded number, but for our purposes, we're going to say yes, include it, because that value exists. I'm going to combine that with the next value that existed, and we saw that was at 1.66, and out to infinity. Okay, and the last piece of information that we have is our continuity. So continuity, we have a whole bunch of different examples of continuity. This first graph that we see, this is not a continuous graph right here. If I were to draw that graph, I'd have to pick my pencil up and then put it back down to draw it. So this is an example of what's called a jump discontinuity. Okay, I have to pick my pencil up and then put it back down in order to draw it, so I'm jumping my pencil. Notice that that discontinuity is happening just at that value A as well. At times we'll discuss removable versus non-removable. Because there's a large set of numbers in between here, in between those 2 points, this would be something considered non-removable. Graph number 2, also discontinuous, because in order to draw that, I have to pick my pencil up and then put it back down. However, this one's called an infinite discontinuity. And again, the reason I have a whole infinite set of values right here at this A, this is like an asymptote of your graph. And again, both of these would be considered non-removable. I can't fill it in. Okay. Number 3 and 4 are very similar. Number 3 and 4, again, still discontinuous. These are called points of discontinuity because there's only one location right here that's discontinuous. Same thing here. Only one location. The only difference with 3 versus 4 is on graph 4, they've tried to define that. They've tried to plug in that hole with a value. So at times, this is how we could see the difference between non-removable with an infinite discontinuity versus a removable where I could put a point. I could fill in the hole. So I could call this removable because I'm trying to define it at that point. Okay. Number 5, this is continuous. This is the only continuous graph we have. Okay, when I trace this graph, I see I can trace this entire graph without having to pick my pen up. Therefore, it's got to be a continuous function. So graphs 1, 2, 3, and 4 were all discontinuous. Graph number 5 was our only continuous function.